So, in the context of CPUs, I have mentioned at an earlier point about how the memory hierarchy of the system, right? We basically have something called the CPU out here. The CPU is trying to access memory, and the main memory that we have over here is usually something called dynamic RAM or DRAM, dynamic random access memory, right? So, DRAM. Now, the problem with DRAM is it can potentially have a very high latency to access, meaning that random access in DRAM is not guaranteed to be fast. What I mean by that is there is a complicated process at the electronics level where you literally have to sort of charge and discharge various electrical lines before you can read data from the DRAM. It means that potentially if I put out an address that I am trying to access from the DRAM, it could take hundreds of clock cycles for the data to come back, right, because the DRAM was not ready and I need to charge it, I need to sort of prep it to get the data out. So, what is done in practice is that we usually put some kind of cache memory in between the CPU and the memory, or this cache is basically a memory block which is between the CPU and the DRAM, but the cache is of a different type. It is usually what is called SRAM or static random access memory. The biggest difference being that SRAM guarantees that if you are reading from a certain location, you will get the data back in a fixed number of clock cycles. Typically with what's called the L1 cache, it would be within one clock cycle, okay. And you do that because you are able to keep the cache size small. One of the main reasons why DRAM has this indeterminacy and large number of clock cycles is because it's able to store gigabytes of data, and just organizing all of that in a way by which you can pull out the data from any given location as quickly as you want is not easy to do. But if you limit your cache size to a few kilobytes or at most megabytes, you can probably put much tighter guarantees and say, okay, either finish within a single clock cycle or at most maybe 2 or 5 clock cycles, some bounded number in other words. So, let us not worry about the levels of cache L1, L2, L3 and so on. Instead, I am going to just assume there is something called a cache. The biggest problem that we have once we have a cache is this cache is obviously not big enough to store all the data in DRAM, which means that at any given point in time, only a small amount of the data which is present in DRAM is sitting in cache, right. Now, what that also means is that as long as the CPU is working with that data, it would prefer to work from cache. It does not want to keep sending the data. It does not even want to, every time it makes a change, I do not want to push it all the way back to main DRAM, because that itself takes another few hundred clock cycles, right. So, instead what I do is I just keep the data in cache, because sometimes what I am doing is maybe it is like a matrix multiplication where I am constantly changing some data. I am multiplying, accumulating, doing some other modifications on the data, right, and I would rather not worry about sending it out to the main DRAM until my computation is finished. So, if that is the case, then what you can have is that there is a coherency problem, meaning that the contents of cache and the contents of main memory do not match, okay. Now, this is not normally a problem because the CPU is always reading from the cache. Great. What happens if another bus master comes into play over here? And I am intentionally calling this a bus master because it could be another CPU or it could be DMA, right. What happens when another bus master comes in and wants to read from memory? The problem is, for this cache to work well, it has to be part of the CPU or very closely tied to the CPU itself, which means that this bus master is not really seeing this cache, right. And what that means is that if I try reading from the same location that was already present in the cache, now I have lost coherency, meaning that the data which is present in memory and the data which is present in cache are not matching, right. So, I have basically become incoherent, right, at this point, and we need to have some way of preventing that from happening, okay. Now, ultimately the sort of to summarize why that happens is, cache memory in general is a fast memory that is hardware controlled, right. It is directly sort of usually inside the CPU block itself. It is meant primarily as temporary storage, right. data in the cache can be accessed much faster than memory. And the question that we have to answer is what happens when two processors or two bus masters in general try to read from a given memory address. Now, as you can imagine, if the CPU has not changed anything, it has only read data from here, we do not have a problem, right? I read data into the cache and then into the CPU, I read data directly into this bus master, I get the same data. But let us say that the CPU changes something in cache, but it has not written it back into main memory. Now when this second bus master tries to read, it reads the wrong data. The other possibility is the CPU has got data in cache, it keeps performing operations on this. In the meantime, this bus master goes in here and modifies some data out here, right? If the CPU doesn't keep on checking, right, every time it has to check, okay, did something happen to the data out here? And that's not particularly great, right? Every time if I need to go back and check, okay, did this data change over here? Then I might as well just read from the main memory. So I don't want to do that, right? So I don't want the other bus master going in and directly invalidating my data by writing something into memory over there, right? So there are a lot of reasonably complicated ways of solving this problem, right? Primarily what happens is that the cache controller needs to sort of snoop on the bus and say, okay, is anybody else trying to modify a given location in memory? If so, it will basically alert the CPU that something went wrong, the data over here is invalid or dirty as it's called, right? So setting this up can be quite complicated, right? The bottom line is this is not going into details of how caches work is out of scope of this course, right? So instead I just wanted to sort of mention why it can lead to problems and why it's relevant for us. So as you can imagine, as far as we are concerned, the fact that our DMA is a secondary bus master is the problem, right? And I need to be able to sort of enforce coherency in the data transfers that happen. So to summarize, if the CPU writes data into the CPU cache, this is not yet in memory, the DMA reads from memory, it sees stale data. Alternatively, the DMA writes to memory, but the CPU reads data from the stale cache. Both of these are problems that we want to avoid, okay? And the solutions that we can think of are essentially defining explicitly that there is something called a coherent buffer, right? And the hardware itself has to be instructed that this buffer, this block of memory is special. You have to make sure that it's kept in sync with the cache, right? Now, in the case of streaming data, very often what we do is we just go for another approach entirely and we explicitly synchronize using certain function calls, right? One other thing which needs to actually happen in the context of DMA, right, which is not directly related to the caches but is still relevant and useful, is that ideally the DMA, remember, it does not have this notion of virtual addresses. In a real Linux system, if I allocate a memory block of, let's say, 1 megabyte, it is very likely, or possible at least, that that data is from different locations in memory. So 500 kilobytes might be from one chunk of memory and another 500 kilobytes from somewhere else. But the virtual memory translation takes care of making everything look as though they were continuous addresses. So in virtual address space they are continuous, in physical address space they may actually be different, right? That won't work for DMA. As far as DMA is concerned, it doesn't know about virtual addresses. So when I am trying to use DMA and I want, let's say, a 1 megabyte buffer, I need to use a separate kind of memory allocation, not just the malloc kind of things that we use in the CPU or in the OS, right? We need to have another set of function calls which are guaranteed to give me contiguous memory. Contiguous meaning that the entire block of memory is one continuous set of addresses, right? So all of these are related to, well, at least the first two are directly related to cache coherency, and this gives us one more issue that we need to deal with in the context of memory allocation for DMA. So to summarize, right, from the point of view of the system function calls that we use inside the operating system, whenever I am using DMA, right, I would probably need to use this DMA alloc coherent as a memory allocation primitive, right, which means that it's not exactly malloc. What I am doing is I am basically asking for the kernel to allocate a certain chunk of memory to me, right, and also to ensure that it is kept coherent, right. So, we are saying that the CPU needs to sort of ensure that any data that I write into this buffer is kept synchronized. Now, understand that that automatically is a potential performance penalty, right, because what it's telling you is that the CPU cannot just use the cache for this block of memory, right, which means that since it has allocated memory, and especially if I am asking for a large chunk of memory, it is going to be somewhere in the DRAM. What the CPU can do is ensure that it is kept coherent, but at a cost, which basically means that it is going to be slow to access or potentially slow, right. Now, streaming DMA is actually saying, we can do something else. I would essentially set up something called a DMA handle, right, where I ask for a streaming map. In other words, take this block of memory and map it into the streaming interface, and then I can use something like DMA sync for device. That is an explicit cache synchronization. It basically says, hey, now perform the synchronization, make sure that what's in the memory is synchronized through the cache or otherwise, but is sent to this device. And similarly, when I do sync for CPU, it says, okay, I am getting data from a CPU, I need to make sure nobody else has got this data in cache, and make sure that the data goes through properly into main memory, right. So, this thing of whether we are using coherent allocation, whether we are using streaming DMA, and in fact in a lot of cases we might actually have to use a combination of the two, so that the buffers themselves are coherently allocated and can be used by other segments of memory, but the streaming is used for actually communicating with the streaming device.